I am Dr. W. B. Gunole from Kamla Nehru Mahavidyalaya, Nagpur. Today we are discussing the structure of benzene in case of aromatic compound. And to determine the structure of benzene, there are different steps, that is molecular formula, evidences for the cyclic ring, and also no state change structure, and resonating structure, molecular formula, and in that case molecular orbital structures. And after that also we are discussing the different Kekule structures and molecular orbital pictures of the structure of benzene. So by using all these steps we can determine the structure of benzene. So the today's topic is aromatic compounds and aromaticity, and in this part number 6 we are discussing today the topics are what is the structure of benzene, and in this we are discussing different steps, molecular formula, no state change structure, evidences for cyclic structure, Kekule structure, resonating structure, and molecular orbital structures of benzene. As we know, the structure of determination of benzene have different steps, and different steps are: first step is the molecular formula, and from elemental analysis and molecular weight determination, it shows that the molecular formula of benzene is C6H6, and therefore it indicates benzene is an unsaturated compound. And again now here that this formula C6H6 shows that benzene has 6 hydrogen atom and less than corresponding saturated alkane, that is hexane, and this indicates the benzene is unsaturated compound. As we know, there are two types of hydrocarbons, saturated and unsaturated. Unsaturated contains carbon-carbon double bonds. So here also it indicates the benzene molecule have double bond, or unsaturated compound it is known. And this is the molecular formula. So molecular formula of benzene is C6H6. Second important point is the no straight chain structure. So now benzene does not behave like alkene or alkynes, but it did not decolorize also bromine in carbon tetrachloride or potassium permanganate in cold, and therefore it does not add water in the presence of acid. And the reaction shown, so it does not add water, and also this benzene when react with the bromine in presence of carbon tetrachloride, no decolorization, in case of cold potassium permanganate no reaction is there, and also it does not add the water. So all these three reactions, so there is no any reaction of bromine, potassium permanganate, or the water, no addition of water. So all this reaction shows that the benzene does not behave like alkene, and they do not have straight chain structure. So there is no addition, there is no reaction, so there is no straight chain structure. This is confirmed from this reaction. And third important point is the evidences for cyclic structure. So if it is a benzene have no straight chain, then it should have, or it may have the cyclic structure. And a cyclic structure can be confirmed from this third number point, that is the evidences for, what are the evidences for cyclic structure of benzene. So benzene can also undergo the substitution reaction with bromine in presence of catalyst and forming monobromo derivative. So the reaction is shown here. Benzene will react with bromine forming bromobenzene here, and HBr, यहाँ से एक यहाँ पे Br आ जाता है. This is the phenyl group, and actually it is a benzene C6H6. यहाँ से एक H निकलता है, उसकी जगह Br और HBr बाहर निकलता है. In this case no other isomeric product is obtained, which indicate that all the 6 hydrogen atoms in the benzene are identical. This is possible only if the benzene had cyclic structure. So the structure, cyclic structure containing 6 carbon and 6 hydrogen attached to each carbon. So benzene can add 3 hydrogen undergoing the reduction to give the cyclohexane. So in this way 3 molecules of hydrogen. So this benzene, 3 molecules of hydrogen, when it is added at this temperature in the presence of nickel forming cyclohexane. एक हर एक कार्बन पे एक एक हाइड्रोजन जाएगा तो क्या मिलेगा? Benzene it becomes a cyclohexane. So it is the evidence for the cyclic structure for the benzene. So no, benzene have no straight chain and also it has a cyclic structure. This fact also shows or confirm that benzene is a cyclic compound having 3 double bond, carbon-carbon double bond. So in case of benzene there are 3 carbon-carbon double bond. And next slide shows that it also shows that each carbon atom is linked to one hydrogen and confirming the molecular formula. So to explain one of them here now, next part is the Kekule structure, and this is the name of scientist who explained the structure for benzene, and it is also cyclic structure. And benzene was given by structure of benzene was given by Friedrich August Kekule. Name of the scientist is the Friedrich August Kekule. He proposed that 6 carbon atoms of benzene are joined to each other by alternate single and double bond and forms hexagonal ring as shown in the here slide. So the Kekule suggested alternate single bond, double bond, single bond, double bond, single bond, double bond. So this can also be shown in this way. So CH, CH, CH is there one hydrogen attached to each carbon atom. So in this way they have the structure, and so this is the structure for benzene suggested by Kekule. So Kekule suggested the benzene is a cyclic planar molecule with a 6 carbon atom linked to each other by alternate single and double bonds as shown in the slide. And Kekule structure is represented as shown here. This is the Kekule structure shown in the slide. This is the structure known as Kekule structure for benzene. And now each carbon atom is linked to one hydrogen, therefore confirming its molecular formula C6H6. However, objection were raised for this structure, and to explain one of them, Kekule modified the idea, and Kekule suggested that benzene was a mixture of 2 forms. So Kekule also suggested these 2 structure. This is one structure of benzene and alternate. Now the position of double bond has been changed. Now this is double bond, this is double bond in this way. So these are the structure 1 and structure 2 are the Kekule structure, structure 1 and 2 suggested by Kekule, and these are the suggested structure by Kekule for the benzene. And he says that this is the mixture of benzene is a mixture of these 2 structures or these 2 forms. So these are the structures suggested for benzene by Kekule. Number 5 point is the regional structure of benzene. So what are the regional structures? So we can say that when 2 or more structures are represented for the single substance with identical atomic position, then the phenomena is known as the resonance. So similars are there, only the position has been changed, then it is known as the resonance structure. So Kekule suggested different resonating structure. Structure 1 and 2, these are the structure 1 and this structure 2, as we have seen, is known as the Kekule structure. And he also suggested that structure of benzene as the structure 1 and 2 suggested by Kekule are actual resonance structure of benzene. Actual structure of benzene is represented as hybrid structure of structure 1 and 2. So this is not one structure for this. So combination of these 2 we get this is the complete structure. So this is the resonance hybrid structure for the benzene. So this is the structure suggested by Kekule. So these are known as the resonance structure. So structure 1 and 2 suggested by Kekule are resonance structure of benzene, and actual structure of benzene is represented as a hybrid structure of 1 and 2 as shown in this slide. And here another structure is also shown in this case, that is the Divar structure. And in case of Divar structure of the benzene, 3 different structures have been shown, and these are the how it is there. So see the Divar structure, these are represented by 3, 4 and 5. So these are the double bonds, and this is the long bond as shown. So this is another structure, this is third structure. So 3 possible structures given by the scientist Divar. So these are not stable. Most stable structure of benzene is the Kekule structure, and these structures are not so stable structures. So here different structures, regional structures suggested for benzene by Kekule and Divas. Now in case of it also been suggested that structure 1 and 2 are the theoretical representation of the benzene, and the actual structure of benzene is the resonance hybrid of the two structure. Actually it is shown that experimentally, and it's shown that in resonance hybrid all the carbon-carbon bond length is a 1.40 angstrom per minute, and calculation Kekule structures are structure 1 and 2, and Diva structures are 3 to 5. Calculation have further shows that the two Kekule structures differing only in the arrangement of electrons and make major contribution toward the resonance. However, the two Kekule structures may be regarded as a canonical forms of benzene. The actual structure of benzene is neither represented by 1 nor 2, but it is a resonance hybrid of these two structures. So it is not a structure 1 and not structure 2, but it is a hybrid structure of the structure 1 and 2. So it is known as a resonance hybrid of the two structure. 6th number point is molecular orbital structure. Now this is also in benzene shows different molecular orbital structures, and in this case molecular orbital theory explain the structure of benzene molecule, and benzene is a cyclic and planar molecule containing 6 carbon and 6 hydrogen atoms. All the carbon atoms are in sp2 hybridization state. In this case each carbon atom, all the carbon atoms are sp2 in hybridization state, and the sp2 hybrid orbital means 3 orbitals are there, 1 s and 2 p, so they are mixing, and 3 hybrid orbitals are there, and sp2 hybrid orbital of carbon overlap with each other and with the s orbital as of the 6 hydrogen atom, forming carbon-carbon and carbon-hydrogen sigma bond. So sp2 hybrid orbital of carbon overlap with the sp2 hybrid orbital of carbon, forming carbon-carbon bond, and also sp2 orbital of carbon overlap with the s orbital of hydrogen, forming carbon-hydrogen bond, sigma bond. So carbon-carbon and carbon-hydrogen bonds are shown by the sp2 hybridized orbital of carbon. So in this way all the carbon and hydrogen atom in the benzene lie in the same plane, and as a sigma bond is formed due to overlap of sp2 orbital. Sigma bond formation in carbon-carbon and carbon-hydrogen also shown here. How the sigma bond is formed? So this is the carbon-carbon sigma bond, this is carbon-hydrogen sigma bond, this is carbon-carbon sigma bond. So all the carbon atoms in this case are in one plane, that is planarity of the benzene is shown. So this is the molecular orbital structure, and in the next slide that further all the 6 carbon atoms in the benzene contains unhybridized p orbital with 1 electron and perpendicular to the ring. These 6 pi orbital have their lobes above and below the planar ring, and therefore the p orbital undergo the lateral type of overlapping. So unhybridized, each carbon have unhybridized orbital, they overlap laterally and forming the pi bonds. So in this case this is also known as the delocalized pi molecular orbital, which are shown in the picture figure. How this sigma bond skeleton of benzene is shown here. So how the bonding is forming. So this is the orbital of sp2 orbital of this carbon, this is the sp2 orbital of this carbon, forming carbon-carbon sigma bond. So here also sigma bond, carbon-carbon sigma bond, and this is shown sp2 orbital of carbon and 1s orbital of hydrogen, forming carbon-hydrogen sigma bond. So 6 sigma bonds are there, 6 carbon-carbon bonds are there, and carbon have 4 orbital. Out of that 3 are the sp2 hybridized and 1 unhybridized orbitals are there on the each carbon atoms, and they show the overlapping. In this way they undergo the lateral overlapping. So carbon, this is the carbon 1, 2, 3. It involved in the formation of carbon-carbon sigma bond, carbon-carbon sigma bond, carbon-hydrogen sigma bond, but this is the unhybridized orbital. On each carbon overlap laterally and forming this type of structure. So in this case, two possible sideways overlapping of 6 unhybridized p orbital is there and forming the pi bond. So by the sideways overlapping, there is a formation of pi bond. So in case of molecular orbital structure, here is shown how the lateral or sidewise overlapping is taking place and the formation of pi bond in the benzene. And because of this lateral overlapping, so see now here how the orbitals are overlapped laterally, and because of that there is a formation of this type of electron cloud here above the plane of the ring and below the plane of the ring. So this is the pi electron cloud lying above and below the plane of the benzene ring. So this is the benzene ring, 6 carbon atom, and one electron cloud, pi electron cloud lying above and second lying below. So these overlap in this way and sidewise and forming this pi electron cloud above and below the plane. So this is the structure, molecular orbital structure of this benzene as shown here. So we can say that benzene does not give addition reaction easily, instead of substitution reaction are preferred. So the stability of molecule is retained in these structures. So these are the different structures suggested for the benzene. So we can say that benzene does not give addition reaction easily, instead of substitution reaction are preferred. Therefore the stability of molecule is retained in this structure. The participation of pi electron in the formation of more than only bond is called delocalization of electron, and this is also known as the delocalization of electron, which make the molecule more stable. If there is a delocalization of pi electrons are there, then it make the molecule more stable. So benzene is a more stable molecule, and in this way these are the different steps to determine the structure of benzene. And so different steps are in this case, different steps that we have seen is the first is the molecular formula is the C6H6. Second is the no state chain structure, and some reaction, that benzene reaction with potassium chromate or what is the bromine, and no addition of water, so indicate that there is no state chain of the structure in the benzene. And also some evidences are there, they show the benzene is a cyclic, having the cyclic structure, that is when benzene react with the hydrogen, then it forms cyclohexane, so indicate that it is a cyclic structure. And also Kekule suggested the cyclic structure for benzene. We have seen structure 1 and 2, and also we have seen the resonance structure suggested by Kekule and the Diwar. And after that also we have seen molecular orbital diagrams of the benzene. So how they form, each carbon is in a sp2 hybridization state, and one orbital, sp2 orbital, overlap with the carbon, forming carbon-carbon sigma bond. Second is forming sp2 orbital of carbon overlap with the hydrogen, s orbital of hydrogen, forming carbon-hydrogen sigma bond, and one orbital is unhybridized on each carbon. This unhybridized orbital on each carbon overlaps sidewise and forming the pi bond. So there is a pi electron cloud above the and below the plane of the benzene ring. So that all these parts we have seen. So this is the complete structure of the benzene, and it consists of different steps. So today we stop here, and we will discuss the some important part of the aromatic compound in the next, that is the Kekule rule and aromaticity. All these part we will discuss in the next part.